Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
Today's science starts out just plain weird. If you can make it through our brain breaking opening stories, you will be rewarded with an interview with Dr. Veselin Kostov, the NASA postdoctoral fellow and SETI Institute research scientist behind last week's announcement of a six-star system that is built out of a suite of three eclipsing binary stars.
Last summer, we introduced you to a weird neutron star named Swift J1818.0-1607. This particular bundle of densely packed neutrons was first spotted flickering in X rays in a way characteristic of a special kind of neutron star called a magnetar, which is a neutron star with an extremely powerful magnetic field. And it was also observed to give off pulses of radio emission, consistent with it also being a pulsar. This combination of characteristics is extremely rare, and astronomers from the ARC Center of Excellence for Gravitational Wave Discovery used the Parkes radio telescope in Australia to perform follow up observations between May and October of 2020. During this time, the star was observed to change in behavior in completely novel ways. It started out behaving like a pulsar, giving off blasts of radio light that were brighter at the low frequency end of the dial. Over time, however, this would change, and by July 2020, it was switching between acting like a pulsar and acting like a more normal magnetar, which gives off radio waves with similar power across all frequencies. With your standard pulsar, you have a fast rotating star, and the magnetic pole of the star is out of alignment. And every time the magnetic pole sweeps past, you see a pulse. With a magnetar, well, we're still figuring that out. But we thought their magnetic and rotational poles were aligned. This star, this weirdo neutron star that appears to be both a magnetar and a pulsar, this star appears to have a magnetic field that is twisted up in a way that looks like nothing we've ever seen before, according to PhD student Marcus Lauer. From our observations, we found that the magnetic axis of J1818 isn't aligned with its rotational axis. Instead, the radio emitting magnetic pole appears to be in its southern hemisphere, located just below the equator. This is the first time we have definitively seen a magnetar with a misaligned magnetic pole. In a new paper in Monthly Notices of the Royal Astronomical Society, with Lauer as first author, the magnetic field is described as having two closely spaced poles that are connected by distorted magnetic field lines. This is like if you shoved a horseshoe magnet into a star with its north and south poles sticking out the side of the star. And if this isn't weird enough, in August, the magnetic field temporarily rearranged itself. Lauer goes on to explain. Our best geometric model for this data suggests that the radio beam briefly flipped over to a completely different magnetic pole located in the northern hemisphere of the magnetar. Exactly what is going on is still being figured out. There are plans to continue observing this wild object to try and understand what behavior is normal and abnormal for it. It's thought this may be a fairly recently formed neutron star, and it could be this is just the normal misbehavior of a star settling into a new configuration. We just don't know. Hopefully, we'll be back talking about this object a third time, explaining exactly what is going on in the not too distant future.
Switching gears, our next story takes a quick look at the ratio of visible matter to invisible dark matter in a nearby dwarf galaxy. Large, healthy galaxies like our own Milky Way, with star formation and a complex structure, are thought to form through the merger of dwarf galaxies. We can observe myriad small galaxies being gravitationally pulled into the Milky Way and shredded as our galaxy consumes them. Researchers study today's surviving dwarf galaxies to understand what went into making our galaxy. One of these dwarf galaxies is Tucana 2, a dwarf galaxy faintly visible in the southern sky. This system has very primitive stars that are 1,000 times less rich in heavy elements than our own sun, and that recent observations revealed to be larger than previously thought. In a new work published in Nature Astronomy with first author Anirudh Chiti, astronomers were able to identify knots of super bland stars far from the galaxy's core. The average star in Tucana 2 has more than 1,000 times less heavy elements than our sun, and these new stars have one third the heavy elements. Since heavy elements form over time inside stars, this implies that the stars in the outskirts formed from more primitive, more bland material than the core. In fact, this dwarf galaxy may actually be the result of two even smaller dwarf galaxies merging, with the two sets of stars coming from different systems. The motions of these stars also allow us to measure the galaxy's mass, and it appears this system has significantly more, as in 3 to 5 times more, dark matter than previously thought. According to co-author Anna Frebel, we have thought that the first galaxies were the tiniest, wimpiest galaxies, but they actually may have been several times larger than we thought and not so tiny after all. The two galaxies, now appearing as one, will eventually be consumed into the Milky Way. It's a galaxy eat galaxy universe out there, folks. After the break, we're going to be looking at some less brain breaking planets. And don't forget, in the second half of our episode, we'll be joined by Dr. Veselin Kostov to talk about that 6 planet system announced last week. Stay tuned. We head out into the solar system with our planetary science now, and our next story comes from a colleague of mine during my internship, so I'm pretty excited for him. Scientists have known for years that Mars once had a thick atmosphere and could actually keep liquid water on its surface. Then it lost that atmosphere to space, and now only has an atmosphere that is 1% the density of Earth's. One possibility for studying that lost atmosphere is by sampling the surface layer of Mars's moon Phobos, which has been bombarded by the escaping atmospheric ions. Those ions of oxygen, carbon, nitrogen, and even argon could be preserved in the uppermost layers of rock. And to make the sampling easier, Phobos is tidally locked to Mars, so the same side faces the planet all the time. So long as a sample is taken from the facing side, it should show evidence of that atmosphere if it has been preserved as predicted. Even better, JAXA has a mission called the Martian Moon's Exploration Probe that is scheduled for a 2024 launch and includes collecting samples from Phobos as an actual part of its mission plan. As scientist Quentin Nanon said, with a sample from the near side, we could see an archive of the past atmosphere of Mars in the shallow layers of grain, while deeper in the grain, we could see the primitive composition of Phobos. The reason we think this idea will work is because it already has with the moon. Samples taken from the moon during the Apollo missions recorded atoms coming from the sun and Earth, creating an historical record of part of the early solar system. With no atmosphere or erosion, the moon's surface provides a well preserved archive for us to research. And the same should be true of Phobos.
Finally, we head out to Jupiter to revisit an old friend of the show, Ganymede. In a new paper published in the Planetary Science Journal, a team of scientists analyzed data from the Atacama Large Millimeter Submillimeter Array, or ALMA, taken at several different millimeter wavelengths to create a thermal model of Jupiter's largest moon. This data allowed them to create a global temperature map and identify a few interesting features. First off, Ganymede gets more densely packed the further below the surface you go, dropping from 85% porosity to 10%. What that means is the more porous the rock, the more easily it responds to changes in heating. So the outer surface will react more quickly than the subsurface rock. That means just a little heat from the daytime sunlight, even at that distance, could have a substantial effect on the expansion and contraction of the surface. Next, There are a few craters that are cooler than expected, which could mean some localized variation in composition, porosity, or even the properties of the grains of rock, maybe even some combination of these qualities. Last but definitely not least, there are a few large scale deviations in the temperatures expected. Excess heat was measured at the equator, and at the middle latitudes, cooler temps. These results likely mean that Ganymede's surface temperatures are mostly influenced by the external processes, such as micrometeorite and plasma bombardment from Jupiter. The team is planning to do future studies using ALMA data, including more analysis of Ganymede as well as Jupiter's moons Europa and Callisto. We'll bring those results to you here on the Daily Space when they are available. After the break, we'll be back with our guest, Dr. Veselin Kostov.
Last week, we brought you the story of a newly discovered system, which, as Pamela said then, is a single star system with 6 stars, arranged in pairs that, like dancers on a dance floor, all appear to circle in the same plane on the sky. The system was found in NASA test data using machine learning software designed to look for eclipsing binary stars. All 6 stars appear as a single point of light that over time varies in brightness from our perspective here on Earth, which means a lot of geometry had to be just right for us to see the various eclipsing stars. We are looking at the system edge on to its orbital plane. The 2 inner pairs of stars are in a relatively tight orbit with each other, and there is a third pair of stars much farther out that shares a common center of gravity. It's definitely a complicated dance and begs the question of how such a system could form in the first place. And now we're going to bring on one of the lead authors of a soon to be published paper, Dr. Veselin Kostov, to the show. Now I'd like to welcome Dr. Kostov. Dr. Kostov is a research scientist for the SETI Institute who works out of NASA Goddard Space Flight Center in Maryland. His research focuses on the discovery and characterization of exoplanets. Welcome, Dr. Kostov, and thank you for joining us today.
Thank you for having me.
So first off, did I summarize the paper correctly? Is there anything you want to add?
Yes, I think you made probably a small mistake saying that the 6 stars are going in the same plane. There are 3 different binaries on the sky, and they're not in the same plane with respect to each other.
All right, good to know. Okay, so we know that TESS it's known as an exoplanet mission, but you're going through these observations looking for these eclipsing binaries. Was this planned beforehand or sort of a happy, we've got the data, so let's try kind of project?
So you're absolutely right. TESS is mostly an exoplanet mission, and we are looking for exoplanets. It just happens that when you're looking for a transiting exoplanets, this is a very specific type of planets. It just so happens that when you're looking for transiting exoplanets, it is very easy to actually catch eclipsing binaries. They're the same geometrical phenomenon, and eclipsing binaries in general are easier to find because the signal there is much stronger. So there is sort of a running joke in the community that the eclipsing binary stars are the vermin of the sky for people who are interested in transiting exoplanets, just because the EBs are everywhere and they confuse you in thinking that this might be a transiting planet, but it's actually an eclipsing binary. Actually, the goal of this project that we started about a year ago is to find transiting exoplanets. And to do this, we needed first to find the eclipsing binaries. As we were going through the data and flagging out the eclipsing binaries, many of them turned out to be more than 2 stars, more than two signals there.
Right.
So what started as a kind of our vetting routine, we wanted to vet out everything that looks like an eclipsing binary and put it aside. It turned into a project on its own, project on multiple stellar systems.
So
and
sort of a combination project. So it was like, we are searching for exoplanets, but we have to do this other thing anyway, so let's enjoy it while we do it.
Exactly. Thanks to TESS, we have the luxury of finding so many new interesting things that we're like kid in a candy store. We find new things and we jump straight into it because there is a beautiful data freely available out there. So yeah.
So the system was discovered with a neural network, machine learning. So can you give us any insight onto how software is being used to discover something this unusual?
Yeah, right. So we use machine learning because the amount of data that needs to be processed is staggering. We
Right.
need to go through something like 60 million, or I think the latest number is 80 million different stars.
Wow.
And of course, astronomers use algorithms have been using algorithms for a long time, and this is kind of our latest new toy to use on the data. And the job of the machine learning algorithm is basically to identify targets that look like an eclipsing binary, and it does a tremendous job at that. It is really fast, and it's really reliable for our purposes.
And how was this particular machine learning algorithm trained? What data set was it trained on?
So we trained the software on the data itself. We had a sample of, a small sample of targets that we know are eclipsing binaries, and we fed that sample to the neural network, and we trained it on the data itself, on a small batch of the data itself.
Oh, okay. So we're going to take a short break, and then we're going to be back with more from Dr. Kostov about this fascinating system. So stay tuned. Welcome back, everyone. So Dr. Kostov is here with us talking about this sextuple system with binary eclipses in pairs, 3 pairs. In general, do these multiple systems with multiple binaries tend to have random orientations, or do they align in similar ways when you look at them?
So this is a really difficult question. It is hard to figure out geometrical orientations, orbital geometrical orientations on the sky between multiple systems. When I say multiple, beyond binaries. When it's a binary, you know what's the orientation of the binary if you see the eclipses.
Right.
However, if you see 2 binary stars, if you see two sets of eclipses on 2 different orbital periods, depending on how close the 2 binaries are to each other, you may get an idea on the mutual inclination. But if they're too far away from each other, it's practically impossible with the current data to figure out the inclination.
Okay. So the stargazers in our audience are likely familiar with the bright star Castor in the constellation Gemini, which is also a sextuple system. How similar is Castor's system to the system in your paper?
That's a question that I probably should have been prepared for. I'm not very familiar with the Castor system. I know it's another sextuple. But don't quote me on that. Actually, I need to read it up. I don't know.
Fair enough. Fair enough. So one of the things I noticed in the paper was that it mentioned that so we have these 2 inner binary pairs circling each other this way, and then we have this third outer pair that's kind of circling and passes the orbit sort of passes between their center of gravity, or through their center of gravity over here. It also, the paper mentions that this outermost pair was likely captured by the inner quadruplet. So does this mean that our ability to see these like 6-way eclipses are kind of a matter of chance?
There is definitely a very high amount of chance here. Or to put it another way, there is a very strong observational bias against finding such systems because you need everything to be aligned with respect to your line of sight. Just to make sure that we all get the correct configuration. So there is a center of mass of the entire system, and the quadruple and the third star orbit around that center of mass. It's
Right.
not like just like there is a center of mass in the solar system, which has nothing to do with the center of the sun. It's somewhere inside the sun. So yes, so the quadruple and the third binary, they orbit around that center of mass. The formation of this system is we can only speculate really about the formation of a system like this based on our understanding of how stars form and how they dynamically evolve. Yes, but our current best guess, and this is a guess, is that there was initially a pair of stars, so just two. These two somehow interacted with a nearby passing star, so a third star that it just happens to be nearby, and they captured each other. So you have two stars that capture a third star, and then each of these stars fragmented into two. So you start with right. You start from the bottom and you build up the system as the system evolves. So this is one hypothesis. It's our best guess. It's as good as any, really. And there are multiple formation scenarios. And of course, to figure them out, we need many more than one system. We need to see many systems at different stages of their formation, so that we can build back the picture. We can build back the story.
We talk about that a lot of the show, how we need multiple systems so we can take pictures of basically what the way we like to phrase it is it's like the car crash. You know, here on Earth, when you have a car crash, you can analyze the entirety of the car crash. Whereas in space, because of the astronomical timescales, you have to analyze crashes in different systems at different points in time to understand how they work all the way across.
Exactly. And they're all different cars. Some of them are trucks, some of them are boats, some of them are airplanes.
So your best guess is sort of, we think, but there's always something that can throw a monkey wrench in.
Of course.
Do these systems that you've been looking at, do they give you any sort of general outline about sort of star formation and system evolution, or is it again still that we need more pictures of the puzzle?
So we definitely do, but from systems like this, we start getting the first clues. So for example, we know that in this system, the three pairs are kind of triplets, which is an interesting formation scenario. If it was a completely random history, you wouldn't expect the stars to be so similar to each other, right? You would expect them to be all over the place. But they're very similar to each other in terms of sizes and masses and temperatures. Of course, different orbital periods. But these are, the first glimpses of what might be the formation history of that system. And actually, this is probably one of the more important things about this particular system, is that because everything else is eclipsing, we have very good measurements, very good estimates on the basic parameters of the stars, like masses and sizes and temperatures and relative brightnesses, which is really the mandatory for building the picture of what happened to the system.
So one last kind of a little bit out there question. What are the possibilities for planets in this kind of a system?
So the inner quad, our best estimate on the orbital period of the inner quad is about 4 years or so. I suspect there isn't much room for planets in there. I suspect the two binaries that are the two binary members of this quad, I suspect are too close to each other for any planet to have a long-term dynamically stable orbit. Even if there was something there, I suspect that
too many gravitational forces.
Yes, yeah. So simplistically, I would say that there is nothing in the inner quad, nothing in terms of planets. The third binary is very far away from that quad. The orbital period is about 2,000 years. So the gravitational perturbation from that quad onto the third binary itself is very weak. So I think there is plenty of space, dynamical space, physical space, stability space to have planets around that third binary. But outside the binary itself, so it can only be a circumbinary planet. It cannot be a planet around.
So you're not, it's not going to be orbiting one of the stars. It would be orbiting both.
No, there is no dynamical room for a planet in between the binary itself.
So the binary pairs are all very close together in all 3 sets.
Yes.
Okay.
Yes, there are a couple of days between 1 day and 8 days.
Oh wow, that is
there is
very quick.
zero room for a planet in there.
Okay. Well, thank you so much, Dr. Kostov. This system is so fascinating. I love talking to you about it. We're out of time, unfortunately. So thank you for joining us. And thank you, everybody, for watching. This has been The Daily Space.